Okay, so let's get started with the course material. If you've got this far, then I hope you've downloaded the Word document, which is a template of all your notes that are going to form through this course. There are blank sections for you to fill in, of course, and I hope that you can do that at the same time as watching these videos, pausing where necessary. In this video clip, we're going to look at sections 1 and 2 of the first week's notes, where we look at the learning objectives of the course and get an overview of the types of materials that we're going to see through the course. But particularly to start with, we're going to look at the objectives, what we're actually trying to learn. So when you're going through the course, bear these in mind. The first is to have some experience of identifying systems with one or more degrees of freedom. So one example, a typical example, is a modern commercial jet airliner. So you'll be aware then that it's a very complex system, lots of things going on and interacting with each other. You've got materials, composites, thermodynamics, fluid dynamics, electrical propulsion, and heating and ventilation and cooling systems. So all sorts of things, all interrelated. And where you learnt about Laplace transfer functions in last year's control and instrumentation course, those Laplace transfer functions are going to be the building blocks that we're going to use to be able to communicate between different degrees of freedom, which doesn't necessarily mean things that can move. It can be variables like temperature or pressure. How all of those different variables can communicate together and create a system model. Now, models are one thing, but appropriate models are the important aspect in this course and in life. If you had a full and complete model of the system, okay, it may describe very accurately how your system behaves, but that's too unwieldy, it's too complex and would take too long to understand for everybody to use. So we need to firstly have an appreciation of appropriate level of detail. One of the ways that we'll see this in this course is by looking at a model of this 767 airliner, but just focusing on one aspect of it, its control of pitch, whether the airplane's pointing up or down, and how we can control that. It's a very complex system. We're going to simplify it and analyze it. We're going to do that first with Laplace transfer functions, but then the second objective is that we're going to be able to investigate these systems using computer simulations. When your level of detail gets so much that writing everything down on pen and paper is too complex, MATLAB, LabVIEW and Simulink are excellent tools for analysing more complex systems, once you've understood how to do it at a simple level first. So we'll see how the behaviour of the plane can be controlled and how it can be modelled and understood. So this is quite a nice hands-on example of simulation. Now, another learning objective is that all simulations and all models are wrong. They're all approximations of real life. So it's really important that we know the difference between theoretical simulations and the real world behavior. And not just to say that sentence, but we're going to see examples specifically of differences that can be modeled and that can't be modeled. We're going to look at non-linearities and how they can be accounted for within your system. So the first section is all about modeling, which is understanding and creating predictions of systems behavior. The second real component of the course is about control, of course. And that means if your system is not behaving as you would like, or if you feel that there's scope to improve the performance to make it faster or stronger, then we're going to look at control schemes that will enable us to measure, to sense and to actuate to improve the performance of systems. Examples that we're going to look at include a nice Formula One Red Bull test car. We're going to look at subsea exploration. We're going to look at a hydraulic system, in this case also used to test a race car, and even things like materials testing, which is in this case about dynamics and will link strongly with the dynamics side of the course. Another key learning objective though is about what can and can't be controlled. So we won't be able to improve the performance of everything, and it's important to realize that and not try to control things that you can't. That's going to be frustrating, wasteful in terms of engineering resources, and ultimately ineffective. So that's another big part of the learning objectives in this course and in life. If you can't control it, you let it go, but you deal with it in the best way that you can. The final objective section is to design interfaces between our simulations and our computer-based models and the real-world systems, so that we can use embedded microcontrollers, the Internet of Things, for example, to control real-world systems. We're going to look at examples there, as with all the way through the course. For example, in electric vehicles, we have batteries, usually placed low down. They generate heat as they're used and charged. So that heat needs to be dissipated and controlled. If the temperature's too high, the battery will function ineffectively, or if it gets too high, it could even then combust. So these things are quite important, and we're going to see how those systems can be understood and controlled. We're going to look at another example of electronic stability control, which is very often taken for granted, but is a real critical safety feature in all modern cars that are on the roads. And it's a very clever system of sensing faster than humans are able to sense whether any of the wheels are skidding, and controlling that skid in real time using active control of the brakes and the throttle. And of course the engine itself of any modern car is controlled by a little microcontroller that's in there. So we have an overall structure of modeling and understanding systems, number one. Designing controllers in theory and using tools that will allow us to do that, number two. And then three, implementing those controllers in the real world. So that gives us a list of overall themes. I won't cover all of those in this video, but just to read, the key thing here though is that these themes in control are not separate one by one, step by step aspects. They're all interrelated. So we're going to see a variety of these different themes in each of the applications that we look at. The conclusion that we reach at the end of the notes is that I hope this course gives you the capability to change those things that you can change, the design skills to account for elements that you can't control, and the wisdom to know the difference